Okay, let's get started. Thanks everyone for joining us, and thanks to Sebastian especially. So I'm excited to welcome Sebastian Krijt today, who joins us to continue our Rocky Worlds discussion series. Just a reminder to stay muted throughout the talk, and at the end there'll be time for questions. And if possible, please turn on video when asking questions at the end. Um, so I'll hand it over to Sebastian now to talk to us about planet formation with ALMA and JWST.
Thanks, Jesse. Thanks for coming, everyone. How's this? Just get rid of your
Oh, good.
you here. All right, great. Can you see my cursor too? I can use it to point at things.
Yep, all good.
All right, awesome. So Rocky Worlds. Here's a picture of my favorite Rocky World, right? Ours. This is a picture I took of my son Tobias not too long ago, not too far from here, from Exeter. This is near sort of Lyme Regis on the Jurassic coast. And this picture, I like this picture because it shows all the stuff we like about our rocky planet, right? We have water on the surface, oxygen in the nitrogen in the air, all kinds of green living things, and maybe even someday intelligent life sort of walking around. And it's not just true today, right? Or in particular on this stretch of the coast, you can walk around for a little bit and very quickly find evidence of life, simple life existing hundreds of millions of years ago, right? These ammonites are 200 million years old or so, so you can get very quickly an idea of how conditions, comfortable sort of conditions, have persisted on the surface of the Earth, at least. So the question then, of course, is this true also on any of these 5,000 exoplanets that have been discovered to date, right? The small subset of the smaller Earth-sized maybe ones that are close to the habitable zone could have also conditions that are conducive to life, but we're not sure, right? They're very hard to study directly. So one way to get more information on what these worlds are like is to try and get a handle on planet formation and try to understand how they formed in the first place and compare that formation pathway to what happened in our solar system, for example. So these cartoons here illustrate sort of the big picture. After a young star forms, it's surrounded by a protoplanetary disk. In this disk, you have gradients in density, temperature, radiation field. This leads to compositional gradients as well. There's lots of mixing going on. Things are moving in, out, up, down. And in the inner few astronomical units, close to the water snow line, where water transitions from being predominantly in the ice phase to predominantly in the vapor phase, this is where we think terrestrial planets form, right? So you start from having tiny microscopic dust grains that were already present in the ISM. These clump together, form increasingly larger pebbles, what we call them, so millimeter, centimeter sized objects. These jump over the meter-sized barrier, form planetesimals, somehow protoplanets, which then, depending on how many pebbles or other planetesimals or gas they accrete, can turn into sort of gas giants, Earth-like planets, rocky planets, or anything in between. Yeah, that's sort of the theory nowadays. So we have a fairly unbroken chain of processes connecting the sort of physics and the molecules in the protoplanetary disks to the sort of final planets. But a lot of open questions in terms of how exactly these are stitched together and how the composition of the planets is inherited from the protoplanetary disk. Pebbles play a big role, though, in this sort of modern paradigm of core accretion. So it's the pebbles that are doing a lot of the migrating, the inward transport in these disks, is the pebbles that are responsible for forming the first planetesimals through the process called the streaming instability, if you're familiar with that. And it's also the pebbles that we can image directly with ALMA. So that'll bring me to my next point. But first, I want to highlight also here that sort of process of planet formation on the top here and protoplanetary disk sort of structure and evolution are very much intertwined, and they influence each other in all sorts of ways. So it's maybe obvious to imagine this arrow here in terms of the disk composition affecting the types of planets that are forming. Maybe you have a disk with a bit more carbon, a bit more water. Maybe it leads to planets that are richer in carbon or water. But this goes the other way around too. So especially giant planets, once they form, they can open gaps in disks and affect the sort of disk evolution down the line. Yeah, so it's very much co-evolution of planet formation and disk evolution. That's the theory. But then to test this and to learn more about how these processes operate in different objects, very powerful methods now are to try to take images of disks with ALMA, right, in sort of submillimeters, interferometer, or with the James Webb Space Telescope that I'll get to next. No, actually, first I'll talk a little bit more about pebbles. So pebbles are important because the degree to which they can flow through the disk is predicted to have a big impact on the masses of the planets that form in the inner parts of the protoplanetary disk, as well as the sort of planetary architectures that you, sort of orbital architectures that you find there. So these are the results of planet formation simulations. This is from a paper by Martin Bezarov from very recent one, building on work by Michiel Lambrechts in 2019. So this is showing planet growth and migration tracks during the pebble accretion phase in the protoplanetary disk, which is then followed by an impact or giant impact phase once the gas disk disperses, ending up with a final planetary system that in this case, for a relatively low pebble flux, leads to a system that kind of resembles the inner solar system. And I'll quantify what low pebble flux or intermediate pebble flux or high pebble flux is. If you have more of these millimeter, centimeter size objects migrating from the outer parts of the protoplanetary disk to the inner regions, you can have more dramatic or sort of more prolonged pebble accretion early on. So these are protoplanets capturing the pebbles and growing in some cases quite rapidly. So you can get slightly more massive early, but in this case, maybe you have a few giant impacts at the end, and you still end up with a sort of inner solar system-like setup where you have a handful of planets with roughly an Earth mass at roughly an AU or so. If you have even more pebbles reaching the inner disk, this picture changes though. Now pebble accretion goes on a bit more until it's halted at the pebble isolation mass. The more massive planets will migrate in more rapidly, and you end up with this sort of broken resonance chain of super Earth or mini Neptune-like planets a bit closer in. So very different from what we have in our solar system, but maybe closer to some of the systems that are commonly detected or have been commonly detected by Kepler, let's say, or other transit missions. Yeah, so the sort of this concept of pebbles drifting in and changing planet formation is very important in simulations. Similar simulations also point out that inward migration of pebbles will change the elemental composition in the disk. So the idea is that you have your icy grains covered in either water ice or carbon monoxide, carbon dioxide ice, moving inwards. At some point, they cross a specific evaporation front or snow line or ice line where the ices on their surfaces are no longer stable, so they sublimate. And as a result, as a function of time, illustrated here on the right, for example, your carbon to oxygen ratio, but this works for other elemental ratios as well, will become a complicated function of position in the disk, but also time. Right? So there's lots going on, but in the inner part, so inside the water snow line, you see, for example, here that this inward migration of icy solids leads first to a strong decline in the C/O ratio, because you're bringing in all this oxygen-rich water ice, and then later it goes up again. So I'll come back to this in a little bit. Yeah, so again, so that's all theory and models. We'd like to see this happen in real life. So we can take pictures of disks with ALMA. You have seen some of these before. This is in the ALMA continuum. So you're seeing thermal emission of these pebbles from the D-sharp survey. And what stands out here is that there's a rich diversity in terms of the sizes of these sort of pebble dust disks, and also their appearance in terms of whether they are more smooth, maybe like these ones, or whether they have a lot of substructure, these deep gaps and rings that perhaps are associated with the gaps carved out by forming giant planets. Sometimes there's even azimuthal asymmetries like spirals. So rich diversity. These are just the pebbles. And then if you take just a single object like HT 1632960 in this case, and look at slightly different wavelengths, you can also map out where the molecular emission is coming from. So again, with ALMA, you can make maps of various CO lines or CO isotopologues or other small carbon and oxygen, nitrogen bearing species. And what you find then, even within the same system, different molecules will have very different appearances. And this is slightly more complicated to interpret than the dust maps, because now you're seeing sort of a combination of variations in the actual molecular abundances, but also excitation conditions. You're also not tracing the midplane of these disks, but probably the surface. You have to worry about chemistry as well. So this is slightly more complicated. And there are a lot of papers out there trying to connect sort of the chemical evolution of these disks and their appearance to the dust evolution. That a lot of them stress again this sort of pebble drift and transport process, but I don't really want to go into that here. What I want to highlight just is that these scales are massive, right? So this scale bar here this is 10 AU. For terrestrial planets, what we're interested in really is what's happening very close to the star in the inner few astronomical units. And for that, the best instrument probably is the James Webb Space Telescope, right? So JWST launched in December 2021. Here's Tobias again watching the launch close to Christmas. I like to show this because I can point out that the JWST is truly a sort of next generation, once in a lifetime facility, right? Because Tobias is 3 here, and when I was 3, long time ago, is when the HST launched. So that was kind of funny. Excuse the I can't explain the hats necessarily. And what JWST can do with MIRI is it can take spectra, right? Has a higher resolving power compared to Spitzer in the infrared. We can work out which molecules are emitting in the infrared, where they're coming from, what their temperatures are, what the abundances are, learn about the composition, really the chemical makeup of the innermost regions of these protoplanetary disks. So I'm very lucky to be part of the JDisks team. So this JDisks stands for JWST Disk Infrared Spectral Chemistry Survey. So it's acronyms within acronyms, but it's all related to doing spectroscopy with JWST. This was originally the sort of amalgamation of 4 Cycle 1 proposals for programs led by Klaus Pontoppidan, Andrea Banzatti, Karin Oberg, and Colette Salik. These were sort of pulled together, and then sort of organically this has grown with the addition of Cycle 2 and 3 proposals and various ALMA programs too. And now it's one of the larger, if not the largest team in the world studying disks with JWST. So there's lots of papers that have come out of this collaboration. I'll just highlight a few to show you some spectra and illustrate what we can learn from them. And then I'll go on and talk about water, which is really what I want to get to. So, for example, if you look at individual systems, there's been some interesting surprises. Here's the remarkable case of SZ114, which is a water-rich disk around the late type M star. Right, so here on top you have the data in black. So this sort of flux versus wavelength part of the Miri's range. Orange is the total model, and in the bottom is broken down sort of molecule by molecule. So this spectrum can be explained by most of the features in the spectrum can be explained by sort of water, CO2, hydrogen cyanide, C2H2. But what's surprising here that there is so much water in the model. So all these blue lines are rotational lines of water. This was surprising because usually these late type stars are more characterized by being very carbon rich. Yeah, so there's a lot of surprises in this. The opposite is also true. Usually T Tauri stars, so disks around sun-like YSOs, tend to be more water rich, but they're also, again, sort of counterexamples. So this is DOR33, which is showing carbon-rich chemistry around the solar nebula analog, right? So now we have all these hydrocarbons around the slightly higher mass YSOs, quite surprising. We also reported this very carbon-rich phase around a 30 million year old, but still accreting gas-rich protoplanetary disk, which has so many hydrocarbons that it forms a sort of quasi continuum here. This disk is very interesting anyway, right? Because this age is very high. Why has this disk survived for so long? It's unclear, but I show it here because what is cool now is that you can combine these different objects that have different ages, especially with this very old JO446b. And you can try from the spectra, from the molecules that are in there, to estimate the carbon to oxygen ratio in the gas phase in the inner disk. And if you trust how we do this, and you trust sort of kind of the age estimates for these objects, then maybe you can see, even though there's only a handful of points, sort of a trend of the C-to-O ratio in the inner disk increasing, or evolving with time. On sort of a million-year time scale. And this is very cool because it looks quite similar. It resembles this expectation from the models that inside the snow line, your carbon to oxygen ratio will decrease very quickly, but then over sort of million-year time scales, it will go up again. So maybe we are seeing some of these processes, this pebble drift, changing the chemical composition of the inner disk in this JWST data. The story is almost definitely more complex because there's the stellar mass plays a role, the local radiation sort of field, disk structure will play a role too. But these are the types of things we can now do. What I really want to talk about though is water. So a lot of the JDisk papers focus on water. I'll give you a very quick summary. Water is relevant, or it's extra interesting because, well, first of all, in the inner disk, we're close to the water snow line. Water has rotational lines all throughout, row vibrational rotational lines all throughout Miri's wavelength range, which is great because it gives us a handle on not just the temperature, but also the temperature distribution in these disks, as I'll show. And water is, of course, very relevant from a planet formation sort of context, right? There's always been these stories of the water snow line being preferential place for planetesimal planet formation because water ice can increase the stickiness of your dust grains, or maybe it can elevate locally the surface density. We want to know how much water is inherited by the planets because it connects to habitability. So one of the first programs we got time on was this one, led by Andrea Panzatti, who proposed to get JWST Miri spectra of a sample of 4 disks, 2 compact ones, GK tau and HP tau. So these are ALMA images of the dust disks around these objects, and 2 very much extended disks, IQ tau and CI tau. And the point then was to try and see if there's variations in the inner disk chemistry, or the appearance of the inner disk chemistry, between these small compact disks and the large extended ones, to try and sort of tie those changes to the influx of material. Because maybe the idea was these compact disks are compact because they have seen more of this inward transport of pebbles and ice. That was the plan. So you see here the four spectra. The compact ones are in black. The extended ones are in gray. You see differences in the continuum in red, and you see differences in the line emission. So most of this is not noise, right? It's rotational water lines, and then there's other molecules mixed in. But we focused in this analysis really on the water. And what we found, I'll show spectra, I'll show an example later. What we found is that the story is not, it's quite subtle. So there's no very obvious differences in the total amount of water that JWST suggests is available in these various disks. The differences come in the temperature distribution of the water that's responsible for the emission that we're seeing. Yeah, so it's quite subtle, and the reason for that is that at JWST's in these infrared wavelengths, we cannot actually see all the way down to the midplane of the disk. So most of the water reservoir is inaccessible to us just because the dust extinction is too high. So we're really only seeing sort of the tip of the iceberg, the surface layer of the inner disk. We're trying to look for differences in the water content in that surface layer. So what I'm showing here is that these are modeled spectra of water, gas phase water at different temperatures, different column densities, and different emitting areas that are kind of chosen to resemble protoplanetary disk. So what you see is that sort of hot water in red emits preferentially at shorter wavelengths, at least in this figure, where this sort of cooler 400K and very cold 150K water will have different ratios between specific emission lines and emit more towards these longer wavelengths. Now, JWST only goes out to 27 or so micron, but still in this sort of 20 to 27 micron range, you can use this to try and tease out what the underlying temperature distribution is that's responsible for creating these spectra. And what we found in Andreas' 2023 paper is that where all four disks, so both the compact and both the extended ones, require a hot component, so something like an 800K component coming from the inner, I don't know, half an AU or so with a column density of around 10 to the 18 molecules per square centimeter. This you see in all the disks, but the small ones, HP tau and GK tau, require on top of that a cold water component that has a temperature a few hundred K lower and has a larger emitting area, and you need this to reproduce the intensity of some of these lines sort of in the longer wavelength, upper end of the wavelength range of JWST. I'll show an example later, and how okay, first of all, it would be great if we could go further into the infrared, right? So missions like PRIMA that can cover sort of everything up to including this plot and further to the right would be fantastic, but at this point we don't have anything like that. The way we interpreted this cold water excess was to say that this is really water, sort of 400K-ish water. This is water directly overlaying the water snow line in the midplane. And the reason this is elevated, or this is visible in these compact smooth disks, is because they have this efficient pebble drift moving material inwards. The water sublimates here, is mixed up through sort of diffusion, and that's where we see it. That's why we see it at these temperatures in the JWST spectra. Conversely, the sort of larger disks with gaps and rings have a less efficient influx of pebbles. So the flux of water crossing this midplane snow line is lower, is much reduced, And as a result, there's not as much of this cold water here, because at these temperatures, it's quite hard to form water in the gas phase locally through gas phase reactions. So we think really to have a lot of water here, you really need to bring it in from the outer disk and then mix it up through diffusion. That's the idea. But those were only 4 disks. And the analysis was only looking at these sort of multiple but distinct temperature components. So we went back last year in this paper led by Carlos at CFA. We expanded the sample slightly, so now we have 7 disks, 4 compact ones, 3 extended ones. So these include the 4 disks from the earlier paper, and then add FC tau S209 and GQ loop. And what you see, so first of all, there's a big range in dust disk sizes that's covered here. Here's the spectra in case you want to see them. Here's the water lines with the continuum removed. Skip over that. I'll just highlight that if we do the same thing as we did in the Andreas initial papers, we try to fit these disks with 2 distinct water components, we find the same results. So on the left here, no, the right one first. On the right one is the full spectrum all the way from 12 to 27 micron. In black is the JWST observations, and then on the bottom is or in purple is the 2-component water model, and on the bottom you have the sort of split up the hot and the cold component. So what you see is that in this extended disk, the hot water in pink does a pretty good job of matching pretty much all the features that we observe. Maybe you need a little bit of this cooler water down here. While for the small disks, GQ loop in this case, yes, you need the hot water to match this sort of shorter wavelength stuff, but then you really need this cold water excess, especially here, sort of longwards of 23, 4 micron, this set of lines here. You really need this excess cold water to reproduce them. But we went a step further here. So rather than fitting this water emission by sort of this bimodal 2-component model, we thought it's more realistic, probably, or it's more physically motivated to try and use a power law or tapered power law, both for the temperature of the water and for the column density. So now we sort of prescribe, we imagine the disk as having sort of the midplane and the surface. It's quite similar to what Til Kuijper does in his duckling model, if anyone's familiar with that. And we imagine there's a radial gradient in the temperature and the column density, and then we allow the sort of that gradient to vary as we do the fitting and retrievals, and the results look a little bit like this. So now for all of these 7 disks in Carlos's sample, we can plot column density of water as a function of radius, and excitation temperature of water as a function of radius. Where I sort of arbitrarily drew this 400 Kelvin boundary to separate the hot water up here from the colder water down here. And what is cool is you can see, first of all, that indeed most of this water is coming from the inner AU or so. And also the temperature profiles that you get are not that far from what you would expect based on sort of thermochemical models of protoplanetary disks. You may say, you may wonder whether this is sort of reasonable to really constrain this without there being any spatial sort of information in the spectra. But it turns out you can test this actually in a very neat and independent way by looking at the Doppler broadening of individual lines. So JWST can just about resolve the line widths in a way that you can see actually the Keplerian velocity component to the line broadening. So you can tease out a radius from the sort of half width, half maximum for different lines in the same system to get the independent handle on where this emission from different temperatures is coming from. So this is very neat, just a brief intermezzo. You can then integrate your water column densities again to get sort of a total mass of hot water and a total mass of cold water in blue, and find that the cold water component, so in blue here, indeed correlates with outer disk size. So this sort of matches that earlier point that small compact disks, so the ones on the left, have more water, more cold water compared to the large extended ones. Okay. I'm getting to the discussion, so bear with me. So again, the water we see in the Miri spectrum is coming from the surface layers in the inner disk. We're trying to connect this to a pebble mass flux crossing the midplane snow line, because that's relevant for planet formation. That is not trivial, but in this paper, we use this this sort of simple expression to connect the two. We imagine that there's some amount of pebbles crossing the snow line. That leads to a cold water mass, or that water is mixed up. You're seeing only a small fraction of the column, and it's destroyed locally in the surface regions on a fairly short time scale due to photodissociation or other chemical processing, or it can even diffuse sort of back, so it doesn't linger all that long. This equation is based on assuming that the water sort of influx is balanced by this rapid removal. So if you believe this equation, you can connect, there's a linear correlation between the mass flux crossing the snow line and the mass of cold water that you can detect, and this is very, very powerful. So all the slides I'll show from now on look like this, and then we'll use this to sort of to lead to the discussion. So if you believe this equation, I can plot snowline pebble flux in Earth masses per year, so material crossing the midplane water snowline, and cold water observed by JWST in micro Earth masses on the same sort of, it's the same scale. And then for the horizontal axis, I've used time or age of the protoplanetary disk, but even though it's quite uncertain. So now we can populate this diagram. First, I'll put this in context though. So micro Earth mass is hard to wrap your head around maybe. So I worked out that actually the Mediterranean Sea is more or less exactly 1 micro Earth mass worth of water. So this is what you should keep in mind. This is the type of sort of the magnitude JWST is sensitive to. So we're seeing sort of Mediterranean seas around YSOs, but in the vapor phase, right? So it's gas phase water. These are the 7 disks from Carlos' paper. I added this long-lived JO446b, and I added one or two others. If you plot them as a function of their age, the cold water in the spectrum, based on the fits that I just showed you, and then the symbols correspond to the size of their dust disk if you were to take a picture of them with ALMA. Yeah, so you see sort of diversity. Usually the larger disks are on the bottom here, so this matches what we said earlier, right? These large extended gapped substructured disks have less water in their inner regions. Maybe there's an age trend. It's hard to see. We'd love to compare it to something, right? So that's what we'll do now. You can compare this, for example, to dust evolution models that were made for protoplanetary disks. These predate all the JWST, so it's quite independent, and they line up actually surprisingly well. So here in blue and purple, there's pebble drift models with either fast or slow drift for a sun-like star, or for M stars. So typically these have high. So now I'm using the left y-axis. These have typically quite high flux and then it decays as the dust reservoir sort of depletes. But it's not too far from the JWST sort of measurements. We can also compare it to these pebble accretion simulations that I alluded to all the way at the beginning, when I said that the magnitude of the pebble flux shapes the architectures of systems that form. So this band here, these dashed lines, are showing the diversity that went into the models that I showed all the way at the beginning. So on the top end of this band, the pebble flux is high enough that you should reach, based on those simulations, you should form super Earth planets that have migrated well inside sort of 1 AU, while the bottom end of this range is showing pebble fluxes that are low enough to halt pebble accretion early and form something that is closer to an inner solar system like architecture. So it's a lot of things that go into those models, but I'm trying to illustrate is that the range of pebble fluxes that they need in those models, so to explain sort of exoplanet diversity, is very similar to the range that we see in the that we infer from the JWST data. So I think that's quite exciting. We have systems that are close to the top end, and we have systems that are quite close to the bottom end. You can also then add a line for the solar system. So this is a line based on a recent paper by Tim Lichtenberg and Joanna Daszkowska. It's showing the predicted pebble flux reaching the inner solar system based on a model that they find works very well in terms of explaining the observed NC-CC isotopic dichotomy, right? So some of you will be familiar with this. If you study carbonaceous and non-carbonaceous meteorites, you break them open, you count the various isotopes of various elements they have. Turns out they fall into different, they sort of fall into two distinct groups, and this is sometimes taken as evidence that there were either two spatially separated reservoirs in the inner solar system at the time of a sort of planetesimal asteroid formation, or maybe they weren't so much spatially separated. Maybe it was a separation sort of in time, and you had two waves of planetesimal formation. This model does a good job of reproducing that dichotomy, but it needs a pebble flux that looks something like this. So again, it looks sort of tantalizing, very close to the systems that we observe, right? And it's not been this predates all the JWST observations, so there's not a lot of tweaking going on here. So I think this is very exciting. We have in one picture JWST observations of inner disks. There's a role somehow played by outer disk structure or size. This connects to dust evolution models, exoplanet diversity and pebble accretion models, and the solar system, right? It all fits into this, but it hinges a little bit on this equation being accurate. Which is not straightforward. So some of the questions I thought we could maybe discuss. Check the time here. Are unless you have other questions, of course, it's sort of what about younger systems, right? All these points are in this plot are for systems older than 1 million years. But actually in JWST cycle 3 and 4, we'll start to populate also this region here. So we'll start to we'll be able to see whether these models that predict higher pebble fluxes early, whether those are actually whether we see any of that in the data. How accurate is this relation here? I have a few slides on that if you want me to talk about it. My former PhD student Adrian has done recently published a very interesting study looking at this in more detail. How does the entire inner disk respond to sort of pebble dust and ice delivery, right? I'm plotting here on the y-axis only this very specific tracer, this very specific signature you can extract from the JWST spectra, the amount of water with sort of temperatures below X 100K, but there's all kinds of other stuff you can learn from these spectra. How does all of that connect to this story? Can we actually reliably extract these numbers from space? This is a good question. what is the impact of substructure? Is it really the disk size that matters, or is it the details of the substructure? And then since we're talking about rocky worlds, or well, not really. Maybe I'll say something about what does this mean for the emerging planet compositions? Yeah, this is tough, right? Because what I've tried to show here is that there's diversity in the water content of these inner regions, but this is the water content in the surface layers in the gas phase, right? So should we expect the sort of the planets forming in these more water vapor rich systems, the rocky planets? Should we expect those to have more water on their surfaces, and should we expect the rocky planets forming in the water poor systems to really have? It's unclear, right? Because the step from gas phase sort of abundances in the disk to actual composition of planets is it's not obvious. You need to worry not just about how water is delivered to your protoplanet, how it's added either through planetesimal collisions or pebble accretion, which have very different sort of volatile loss mechanisms. And then later on, during sort of any potential giant impact stage, you have to worry about how the water and other volatiles then partition between the sort of the atmosphere, proto-atmosphere, and the magma ocean and the core. And it's not so obvious to me how this goes, but these are all things we can discuss. So maybe I should stop there. Can leave this up. Feel free to ask about this or anything else. And thank you for listening.
Awesome. Thanks, Sebastian, for a really interesting talk. I guess we have time now for discussion and questions. So please raise your hands if you have a question or type it in the chat and I can read it out. I guess I can also start it off. Ollie actually had a question before he left. So he was wondering about the CDO ratio results that you showed. I think in the plot you showed the increasing C2O for later or older disks or later times.
Yeah.
But they never reached the elevated values of the observations. So he was wondering what was kind of going on there.
Yeah, excellent question. Excellent question. So he left, but I'll answer it for the rest. So indeed, so the what is striking the difference here is that these models, none of them actually in this particular model exceed the CD overall ratio of 0.7 or so. So you're always well below 1, while these systems here do appear to be pushed to sort of values greater than 1. So there's yeah, it's a very good question. So first of all, this model is for a sun-like star, where here I've combined various ones. So you could imagine this looking different for different stellar type. But more important maybe is that the evolution here is driven only by variations in the pebble flux across the water ice line. So you're delivering oxygen, which plummets your sea erosion, then it comes back up as the water goes away, and you're left with, I don't know, CO2, other things. But one process that is not included in this paper and it has been getting more attention is also the destruction of refractory carbon grains. So if you were to extend this horizontal range a little bit further, you would get close to what some people call a soot line, or sort of a line where refractory carbon can be destroyed, and that could also very much drive your C2O ratio then up, because you have an additional source of carbon that you have to take into to account. Other reasons could be maybe luminosity outbursts by sort of young eruptive stars could push this sort of soot line outwards. That could have a lasting effect on the C2O ratio. But yeah, excellent question.
Oh, Rob?
Yes, thank you so much, Sebastian. It was a really interesting talk, really interesting results. But actually, well, you kind of already pose my question on your final summary slide.
Yeah, that's okay.
But I am wondering, like, to what uncertainty do you have on these inferences of pebble flux based on your cold water reservoir? Like, can you already make some inferences of like order of magnitude uncertainties that you have for these disks?
Yeah, it's a good question. It's a good question. So there's two parts sort of to it. One is understanding well what our uncertainties are on the cold water mass that we derive from the spectrum. That's step one, right? So you should imagine all these points having sort of vertical error bars that in some cases can be quite large, and understanding well how those error bars are connected to what we assume for these radial gradients, yes or no, and how exactly we do the modeling of the spectra is one aspect of that. And then the second one is, what about this equation then? How can we really sort of one-to-one, can we really connect the this cold water mass to the current pebble mass flux? Yeah, it's an excellent question. So I can show one thing in that. So derivation of this equation assumes the only source of water is this sublimation of icy pebbles, but you may also form some within the gas phase. So that's sort of missing. And then you're assuming that these constants are the same across various objects and don't evolve with time, and at least one of them will certainly evolve with time. So this eta parameter here is the fraction of the column locally that you're sensitive to with JWST. So what tiny slither in the top of the disk can you actually contributes to the emission spectrum? And what Adrian showed, so I didn't have time to really show this, so thanks for asking. What Adrian showed is that actually if you include not just the influx of water, but you also worry about the influx of hundreds of Earth masses of pebbles that are then destroyed, and that will change the opacity and the extinction in the inner disk. That this sort of tau is one-ish sort of layer will move up and down, and you actually, even though you're bringing in more water and you're enriching your inner disk with water, you're also at the same time hiding more of it because you're adding great sort of more small grains, and this can very much confuse or complicate this neat sort of one-to-one correlation. But then there's other things missing from these models, so yeah, it's very much work in progress. But I was reassured by when I first plotted this by the degree to which these actually this cold water using this equation overlaps with what we think we know about pebble fluxes in disks, right? So I think sort of something seems to be working despite some of these open questions. Yeah.
Sounds like you have your work cut out for you. Plenty to do.
Yeah, lots to do for sure.
Well, yeah, thanks. I guess it doesn't seem like there's more questions, so we'll go ahead and stop there. But thank you so much for your time and for sharing with us today.
Yeah, sure. Thanks for having me.
For the people that are still here, our next talk is June 5th. We'll be hearing from Mike Wong from Carnegie. Yeah, thanks everyone for joining. See you next month.